Hi everyone, let's start week 2. In this week, we will have the remaining of lecture 1 or chapter 4 of our course, and we will cover the rest with 4 parts. So we will have uh, parts 4, 5, 6, and 7 of our chapter 4. This is the first one, part 4. Inclusion of order lead time. If you remember in the basic EOQ model that we had in the previous week, we didn't consider lead time. So we assume that whenever we place an order, we will receive that order right away. So there is no period, there is no lag time between uh, placing an order and receiving that order. But that's not going to happen in the real world, right? We know that there is a time period between placing an order and receiving that order in our inventory. It takes time. It takes some time, and we call this period of time as lead time. Okay, so what if we consider lead time? I mean, we have lead time. So what will be the impact of having lead time? Um, the impact it will be on the reorder point, not on the quantity. I mean, having lead time or not having lead time will not impact on the order size, but it will impact on the reorder point, on the time of placing an order. Because here the matter is the time. It takes time to receive that order, so we need to reorder, I mean place the order uh, a while prior the time that our inventory level becomes 0 in order to have that inventory right away, that time, right the time that inventory level becomes 0, right? So and here we consider the reorder point. For example, in our previous example, if we assume that the orders arrive after 4 months in our inventory, so when should we place uh, the order? What should be the reorder point here? So the solution is obvious, right? It's clear that we need to place our orders 4 months prior the end of the cycle. The cycle time is the time between two consecutive orders, right? So since the lead time here is 4 months, so we need to reorder, place an order 4 months prior the end of the cycle. Okay, so that's obvious, right? But if it's convenient to present the reorder point in terms of the inventory level, so it will be R will be equal to lambda times tau. So tau here is the lead time period, and the lambda is the annual demand rate. So if we multiply this time period by the lambda, then we will have, I mean, the reorder point in terms of the inventory on hand. Okay, so in this case, R becomes this. As you remember, lambda was 3,120 units per year. So tau, the lead time here is 4 months. So since the demand is in year, so we need to transfer the lead time into year as well. So 4 divided by 12. So at the end, we will have 1040 units. So anytime that inventory level reaches to this point, 1040, we will place our order. Okay. So in that example, if you remember, the cycle time was 1.24 years. And now here, the reorder point is this point. When the inventory level reaches to that level, I mean, the requirement to satisfy the demand of 4 months. So that point is our reorder point. So in this point, we will place our order. So let's say here we place our order, and let's say this is the inventory level in terms of the inventory on hand and inventory on the way. Okay, but here it's delivered to our inventory in this point, so the inventory on hand increases to this level. Okay, so Yeah, this is how it works. So we just need to obtain a reorder point here. What if the tau is greater than t? I mean, what if the lead time is longer than the cycle time? So let's have an example here. Let's assume that EOQ here is 25 units, lambda is 500 units per year, and tau is 6 weeks. So here, if you see the t, the cycle time, will be q divided by lambda, so 25 divided by 500, it will be 0.05 year or 2.6 weeks. So the cycle time for ordering is 2.6 weeks, but the lead time is 6 weeks. So as you see here, tau divided by t, the lead time divided by the cycle time is 2.31. So this means that we do have 2.31 cycles in the lead time. Okay, so this means that every order should be placed 2.31 cycles in advance, right? So this will be equivalent, I mean, ordering 2.31 cycles in advance will be equivalent to ordering just 0.31 cycle in advance. So in other words, R, the reorder point, will be 0.31 times 2.6 divided by 52, because it's in terms of the week, so we need to transfer this to a year divided. So we divide this by 52, and then we multiply this by 500. So it will be 7.75, or let's say 8 units. So let's see why 2.31 cycles in advance is equivalent to just 0.31 cycles in advance. Let's have the procedure here first, and then I will explain the reason of equivalence of 2.31 and 0.31 on a figure in the next slide. So here, whenever we do have tau greater than t, we need to apply this procedure. So at first, we determine the number of cycles in the lead time by dividing tau by t, and then we will just consider the fractional remainder of the ratio. Okay, and then multiply this fractional remainder by the cycle length in order to convert back to the unit time. Okay, and then we will multiply that that result by the demand rate in order to obtain the reorder point. Okay, so now let's see why in our example 2.31 is equivalent to 0.31. So here, let's say we need the demand. We need our order to be delivered in this point in our inventory. So we need to place the order 2.31 cycle in advance. So this will be 1 cycle, 2 cycle, and 0.31 cycle. So if we place our order at this time, we will have it right here, right after 2.31 cycle. So what if we have this ordering mechanism every cycle? So the order that we place in this cycle will be delivered to our inventory here, right? And then again here we will have another order, and it will be delivered to our inventory next cycle, and again this point, again next cycle. So by having that every cycle, we will have a delivery in our inventory. So as you see here, this means that considering 2.31 cycle for reordering is equivalent to 0.31 cycle. Okay, I mean the reorder point is exactly the same for both. Okay, the EOQ sensitivity. So let's here have a sensitivity analysis that if we not order with the size of Q star, I mean the Q star here or EOQ is the optimal order size, right? So what if we order a different size? I mean less than Q star or greater than Q star. So what will happen? What will be the impact on our inventory cost? I mean total cost. So here, if we assume that GQ here is the total cost under a Q, not Q star, if we just order in Q size, not Q star, and G star here is the total cost with ordering Q star, I mean EOQ. So the G star here is the optimal or the minimum, actually the minimum total cost by ordering EOQ and GQs in general. So it will be this equation. Okay, and how we get this, you will see here how we get that equation. So let's see how it works. In our previous example, we had Q star EOQ as 3,870 units. So let's see what would be the impact if we order in sizes of 1,000 units, not 3,870 units. So based on the equation that we do have for sensitivity analysis for EOQ here, the ratio becomes 2.06. So this means that GQ will be 2.06 times G star. Okay, so if we call this, let's say, as the ratio, so GQ will be G star times the ratio, right? So in this case, in this example, the GQ, I mean the total cost under a quantity different than Q star will be 2.06 times of G star. Okay. And if we want to calculate the extra cost here, the extra cost will be this. So we do have this equation, GQ equals, let's say, the ratio times G star. So if we subtract G star from the both sides of this equation, we will have GQ minus G star will be ratio times G star minus G star. So it will be GQ minus G star will be G star times ratio minus 1, right? So this is the general equation here. And for this example, we do have this GQ minus G star, ratio minus 1 times G star will be 2.06 minus 1 times G star. So it will be at the end $20.51. So the extra cost in this example, if we order a different amount than Q star, so we will have extra cost of $20.51 per year. Okay. EOQ and just-in-time. So let's have a comparison between EOQ and just-in-time. The philosophy behind the just-in-time is this: reducing the inventory level to a bare essential. So yeah, I mean the ideal situation for just-in-time is zero inventory level, having no inventory at all. So zero, that's the ideal situation, but maybe the applied situation is having a bare essential inventory level. Okay, so if we want to have just in time, so we need to reduce the setup costs. So if the setup cost for ordering or for changing the setup of the production line is high, then just in time wouldn't be a good solution. So yeah, in just in time, we assume that the setup costs are too low. So if we have a lower setup costs in EOQ, then it will lead us to actually reduce the order size by ordering more frequently, right? Yeah, when K, I mean the setup cost, ordering cost is too low, then the solution will be having smaller quantity for ordering and having more frequently orders. Okay, so in this essence, as you see here, EOQ and just-in-time are compatible, right? But not in general. So the principles underlying EOQ and material requirement planning that we will have later in our course are sound and should not be ignored. So we can't say by having the just-in-time we don't need EOQ. It's not working anymore. No, that's not right. That's not true. So we can't ignore EOQ and MRP here, and we'll see why in one example in the next slides. So, and in some situations, implementing just-in-time could end up with higher cost than EOQ. We'll see in our example in the next slide. So here, let's have an example here. Here we have a manufacturer of office furniture located in New Jersey, and it needs a special screws for producing the furnitures. Okay, so the purchase price for the screw is just 3 cents each, and the demand producing 200 discs per month, and each disc requires 40 screws. And the fixed cost here, fixed ordering, shipment, and storing cost is $100 per shipment. And the variable cost here for inventory, we consider 25% interest rate in total. So the lambda, demand for this screws per year will be 200 times 12 because it's monthly times the number of months and the number of screws for each furniture. So we will have 96,000 units. And K here is $100 and H is 0.25 interest rate times 0.03, so 30 cents the purchase price. So it will be this number per unit per year. So by having these numbers, EOQ becomes this 50,597. So if we calculate the cycle time, it will be almost 6 times. This means that 2 shipments per year. Okay. So now, as you see here, the optimal inventory cost here, GSR, becomes just $400. So now what if we consider the just-in-time approach here? So in just-in-time, and if we consider we are going to order the requirements for every week here, not having the ideal solution as zero level inventory, but we'll have a minimum level inventory by ordering the requirement for a week. So in this case, we'll have 52 shipments, 52 orders per year. And in this case, just the ordering cost and just the setup cost will be $5,200, right? It's a huge number, right? In the optimal EOQ, the total inventory cost, inventory holding cost and ordering cost is just $400. But here it's just the ordering cost becomes $5,200. So as you see here, in this case, EOQ policy is much better than the just-in-time. So this shows that if we don't reduce the ordering cost, the setup cost in an environment, in a company, then we can't implement just-in-time philosophy over there. So if you want to go with just-in-time, we need to find some ways to reduce the setup costs and ordering costs in order to be feasible and justifiable to have the just-in-time solution. Okay.